Well, thank you. It's very nice to be here. Is this on now?
Just turn it on the top there. See if there's a little switch on there. Oh, up the top there. Should be on.
Is it on?
Yeah, let's give you a little more volume.
Is that enough volume?
Yeah, now you're good.
Okay, and then I hit this to show?
Yep.
Oh, it's okay. All right, well, anyways, it was very nice to be here, and thank you for a very generous introduction. And, you know, the other point which Carl graciously didn't say is that actually my most cited paper is the one I'm most embarrassed by. So this project is in collaboration with my former PhD student, Alan Gable. We wrote one paper on this, and then I found that Aaron Clausette was doing similar work, and so we joined forces together with his graduate student at the time, Marina Kogan. And so we are just trying to ask a really simple question. Is basketball scoring a random walk? And let me just ask to get a sense of the audience. Who here likes basketball? Okay, notice that my hand did not go up. Who cannot stand watching basketball? Okay, so the point here is that I cannot stand any kind of sports. I mean, baseball, basketball, I mean, it's just stultifying. But what I really love is sports statistics and analyzing it. And so you will see here that I think there's some nice things that you can look at, and you know, I think we've just barely scratched the surface of what we can do. So first of all, maybe I should put on some volume here. Let's turn up the volume a little bit. So this is not a very good quality video, but for those of you under the age of 50, this guy here is known as Julius Erving, Dr. J. And he's doing a maneuver that, I mean, you know, I couldn't even begin to dream about. He's taking off way before the foul line, and he's dunking the basketball. This is called the rockabye baby because he's rocking the baby before he slams the basketball into the basket. And this guy here is Michael Cooper, who is known as one of the foremost defensive specialists in the NBA, who could stop anything. And you see that at some point he's going to contest, and at some point he says, "Holy smokes, get me out of here, I'm going to get crunched." So anyways, this is what basketball looks like to the basketball fan. People with amazing athletic training, amazing coaching, amazing, you know, technique, and they can do feats of athleticism that we can't ever, you know, we can't even dream about. So that's maybe the sports fans' view of basketball. Here is my view of what basketball is, and please excuse my crummy cinematography. This is the Sid Redner School of Cinematography. So I'm flipping a quarter over and over again. So for me, this is what basketball is. It's just repeating the same thing over and over again. A basketball play, you know, you flip the coin, either it's heads or it's tails, which means either you score or you don't score, and you just do this over and over again. That's all that basketball is to me. And what I'm going to try and convince you of in this talk is that this picture of basketball is actually a little bit more accurate than the picture of Dr. J doing the dunk, because not every basket is an amazing athletic dunk event. Anyways, so that's where I'm coming from. So let's look at the data. So what we did, I guess this is a data science center, so I have to say that. Let's look at the data. So what we amassed was roughly 10 seasons of NBA basketball scoring statistics. So we have every single game, we have a trace. You know, it starts off 0-0 at time equals 0. Then at some point in the game, at 7 seconds, a basket is scored. It becomes 2-0, and then it becomes 4-0, and then 4-2. And every single scoring event, we have the data, and so we can then start looking at some statistical measures of basketball scoring. So here is like a typical basketball game. So I had thousands of games to look at, and so I just pulled out one game at random. This is Chicago-Denver. Played in November of 2010. And so what you see in this game is that it starts off 0-0. The game lasts 48 minutes, which is 2,880 seconds. And Denver races to this huge lead. And so they're leading. Here's the first half. They're still leading. And then somewhere in the third quarter, Chicago mounts this furious comeback. And then they take the lead. And then there's a little bit of fluctuation here. And then a bunch of lead changes at the end. But finally, Denver wins by 1 point. And what, you know, if you just look at this as kind of in your first exposure to random walks, it's a natural question to ask, well, here's some signal. The displacement is a function of time, and it's fluctuating, and it's above the line, and then it goes below the line. So here's the question. Is this a random walk? So the whole point of this talk is to try and answer that question. Is this trace a random walk when I average over all basketball games? Okay, so the first thing you can do is, do the most rudimentary analysis. And so here is one of them, which is I'm looking at the scoring rate, the probability that there's a score at t seconds, at the point of t seconds in the game, as a function of the position, the time point in the game. And so what you see is that this scoring trace, so the scoring rate at every single second of the game, it's a fluctuating signal because it fluctuates from second to second. But roughly speaking, there is more or less a flat level here. And if some of you are a little bit more critical, you might say, well, what's happening at the end of the quarters and the end of the game? I will come to that. But roughly speaking, there is an average level, which is roughly 0.33. And that corresponds to roughly a score every 30 seconds, which is what you normally think of in NBA basketball because there's a 24-second clock. If you don't take the ball up the court and take a shot that actually hits the rim, you lose possession of the ball. So there is an incentive to try and score, to at least launch a shot within 24 seconds. And so this scoring rate roughly accords with that feature because not every scoring attempt is successful. And so there's an average scoring rate of about 0.33. So that's one point, is that it seems like there is if I average over all games, there's an average rate of scoring. So that means, like in the context of flipping a coin, it just means that I'm flipping a coin at a constant rate. And it can happen anytime during a game. Now, another thing which is interesting is you could ask, what is the time between successive scores? And more generally, if you're someone who does statistical analysis, instead of just looking at the time between the scores, you look at the distribution of times between the scores. And so here I'm showing you, as a function of the time between the scores, the logarithm of the probability that a scoring event has occurred. And what you see here in the data is that for less than roughly 30 seconds, well, first of all, the probability of scoring immediately after a previous score has occurred is very small because if one team scores, it takes some time to get the basketball down to the other side of the court and score. Sometimes there's desperation, full court shots or full court passes. So you see that the probability of scoring immediately after a previous score is a factor 10 to the 3 smaller than the typical event. But roughly, this probability increases until you reach roughly 30 seconds. And beyond 30 seconds, the distribution is this is on a semi-log plot, is showing a straight line. So it suggests that the distribution times between scores is actually decaying exponentially in time. Question?
Seconds here is game clock?
Yes, this is all game clock. This plot is shown where I don't pay attention to which team has scored. I'm just saying that there is a bunch of scoring events. I don't care if it was the Warriors or the Supersonics, if they were playing each other. I'm not paying attention to who's scoring. I'm just asking for the time between scores. And you see that it seems to fit an exponential. If you look at just single team scoring, so say that it's the Supersonics playing the Warriors, so I look at the time between successive scores of the Supersonics, and you see that it's the same as either team scoring. The only difference is that the x-axis has been shifted roughly by a factor of 2. And in fact, in all of our data, the longest time between one team scoring was more than 1 quarter. So it was like 700 seconds. So the upshot of all of this is that the probability that there is a delay between scoring events of delta t is decaying exponentially. So this is at least a piece of evidence that seems to suggest that scoring is described by a Poisson process, that it's just random when the next team is going to score beyond the 30-second mark. So this at least is the beginning of evidence to argue that this is kind of a random walk-like process because the scoring rate is roughly constant. The time between scoring events is given by an exponential. So this would be what's called a continuous time random walk. When usually when you're first exposed to random walks, you think, well, every single step, every single time unit, I take a step randomly to the right or to the left. But a continuous time random walk is you flip a second coin, which tells you how long you wait before you make the next step. So this seems to be described by a continuous time random walk. However, when you have to look a little bit more carefully to really verify this, because you might imagine that, well, if a team is really hot, that if they score, then because if it's a hot team, that means that the time between the next scoring event should be smaller. So the next natural thing to try and look at is the correlations between the scoring events themselves. And it turns out that this is actually a very controversial and important subject because maybe some of you have heard this notion of the hot hand, that when Stephen Curry is really hot, and is scoring from like way out downtown, give him the basketball again because he's really hot. And so you can ask, is there really a hot hand in basketball? And it turns out that even though most people feel that a hot hand is a natural thing that occurs, it turns out that there really is, at the level of like 10 to the minus 6, there's no hot hand in basketball. And there's this very beautiful paper by Gilovich and company in 1985 that's actually a delight to read. And they have some really great quotes in there. And one of them is that common experience is a very bad indicator of statistical regularity. So when you think you feel something, you really don't. And so what we were looking at then was the correlation between scoring events. And so let me define a correlation function. So here, TK is the time between so I have like my scoring events are a bunch of discrete points, and I have the kth interval between the scoring event, at k minus 1 and k. And I look at the correlation function between the kth scoring event and the k plus nth scoring event. So this is a correlation function, C of n, which tells us that if I have a scoring event over here and another one n down the road, how are they correlated? So if teams are really hot, you would expect that this correlation function, it should be that if there's a small time here, there should be a small time over here. Or if teams are really cold and there's a long time between events here, then further down the road, it should also be a long time. So I would have thought, before I looked at the data, that this correlation function would be something that would decay with n in some way, that it would go to 0 when n got large, and it would say, well, the correlations decay. But in fact, there's no correlation at all. This has been normalized in such a way that at n equals 0, this is equal to 1. And you see that once you get beyond self-correlation, there's a constant correlation coefficient, which is less than about 0.03. So it appears that there's no systematic correlation in the data. So it seems that all scoring events are purely random events given by continuous time random walk. And so this is at least the beginning of evidence to try and argue that basketball scoring is described by a random walk. Here's another thing which is maybe more familiar to most of you, which is if I look now at the variance in the score difference. So the score starts off 0, 0. And the score is then fluctuating randomly, just like a random walk is. And we all learn from elementary random walkology that after n steps, the mean square displacement is growing like n, or the root mean square displacement is growing like square root of n. So what I'm plotting here is this mean square displacement, sigma squared, as a function of time in the game. And you see that at the beginning, and through most of the game, it's looking pretty well growing linearly with time. So the fact that the mean square score difference is growing linearly with time is another piece of evidence that suggests that this is governed by a random walk process. Now, just so you know, there's something here that I will save to the end of the talk. But there's a few places. If there's any, I've given this talk a number of times, and when there's a real basketball fan in the audience, by this point they're getting apoplectic with me because it's like you'll see I've been sweeping some things under the rug, but I'm going to bear them out as the talk goes on. Anyway, so this is another piece of evidence that this is a random walk-like process. Now, it turns out that if you are a basketball fan and the game is a blowout, then you turn off the TV after 3 quarters and you go out for a pizza because it's a blowout. So the interesting parts of any game, and in fact, the only times I ever watch a basketball game is when it's pretty close. And so when the lead changes is where it's the most interesting point of the game. And so I want to now spend the next few minutes describing some features about lead changes because they're the most interesting part of the game. And as you'll see, there's some really nice data that one can analyze in this framework and get some beautiful quantitative results that show the connection between the scoring statistics in basketball and random walks. So I want to focus on just lead changes in a basketball game. And you can imagine if you were just like asking to characterize lead changes, what can you ask about? And here are 4 basic questions. How many lead changes occur? You can read the rest of them. How long does one team lead? When is the lead safe? So if you're interested in game time betting, does anyone do game time betting? No Britishers here, huh? Well, if you want to bet during the game, then you want to know when is the lead safe. So all of these questions, again, can be understood in the framework of simple random walks. So first of all, let's talk about the number of lead changes. So here what I'm showing is a typical trace of score difference versus time. And so the game starts 0-0, and it's doing some signal like this, and there's a final score in the game. And there are these 4 points where the lead changes occurred. And now we can ask, well, how many lead changes should we expect in a typical basketball game? And what is the distribution of the number of these lead changes? These are natural questions you might ask given the data. So first of all, let's do the most simple-minded thing in terms of just a pure random walk. And I want to ask, when I just say pure random walk, is anybody uncomfortable with that term? Nobody's uncomfortable with that term, so good. I'm at the right level. So if I have an n-step random walk, and I ask how many times does this n-step random walk come back to the origin, which it corresponds to a lead change, the number of lead changes, the number of returns to the origin scales the square root of the number of steps in the walk. This is a very basic result in the theory of random walks, and let me just show you where it comes from. So if I have an n-step random walk, the probability distribution is just Gaussian function. And if you want to ask how many times you're at the origin, basically what you want to do is you want to integrate from time 0 up to n steps the probability that the random walk is at the origin at some earlier time. So you integrate 1 over square root of n dn, you get square root of n. So this is why you'll typically have square root of n lead changes if you had a pure random walk process. So just to give you a feeling for numbers, in a typical NBA basketball game, again, modulo some small variations. A typical game is like 100 to 100 is the final score. Each scoring event is roughly 2 points. So it means that there's roughly 100 scoring events in a typical basketball game. And if there's 100 scoring events, there ought to be 10 lead changes. But now here comes the first but about that makes this not a pure random walk process, but we can still analyze it mathematically. Basketball scoring has a different feature, which is the notion of anti-persistence. And what I mean by anti-persistence is that if team A scores, then what happens what happens afterwards? Team A scores, the ball is given to team B, and team B has the possession of the basketball. So there's an inherent advantage for the team that just got scored upon to score next. And that's what's called anti-persistence, in the sense that if team A scores, it's more likely that team B scores next. And it turns out that if you average over all NBA basketball games, the probability that team B scores next happens with a probability roughly 2/3. The probability that you will score twice in a row is roughly 1/3. And by the way, back in the early days of basketball, and this is part of the reason why really old basketball is impossible to watch, is what they used to do is you'd score a basket, and I think I'm old enough that I still remember it, but I'm not sure how many of you would be old enough to do it. But what would happen is that the ball would go back to the center, the referee would throw up the ball, and they'd jump for the ball. So you'd start again from fair initial conditions. So it was like a soccer game or like a hockey game. But that made the game impossibly slow. And so what they've done now is that you just get the ball after you've been scored upon. But this feature of anti-persistence, so now if you think about a random walk in which if I make a step to the right, that means, I'm stepping to the right here. That means 2/3 of the time I'm going to step to the left, and only 1/3 of the time I continue in the same direction. And you can see right away that if I make a step in this direction and then I'm more likely to go backwards, it means that I'm not going to diffuse as far. It means your diffusion coefficient is going to be smaller. And it turns out that if you write down the actual microscopic evolution equation for the probability of the distribution of the random walk, which I'm not going to do here, but if you were to write that down and work out a little bit of detail, you'll find that the diffusion coefficient gets renormalized by a simple factor of 1 minus p divided by p. So when p is roughly 2/3, this factor here is 1/2. So the diffusion coefficient is half as big for an anti-persistent random walk as it is for a pure random walk. And so that means that the number of lead changes actually is, and I said this exactly backwards, this factor is 2, not 1/2. And so it means that the number of lead changes goes up by a factor of square root of 2. So that's first point is that if I had a pure random walk process and 100 scoring events in a game, I expect 10 lead changes. Now, because of this anti-persistence, I expect 14 lead changes. One can actually extend this analysis much further and compute the probability distribution that there are m lead changes in an n-step random walk. And this is just a Gaussian distribution with a characteristic number square root of n. This was first derived by George Weiss in '94. We can do the same thing with anti-persistence, where we just put in this renormalized diffusion coefficient. So again, it's a Gaussian distribution. And now let's show some data to try and compare this with. And so here what I'm showing now is the NBA game data is the red triangles. And so you see that it kind of looks like a Gaussian-looking distribution. And so I'm comparing it with two different things. One is we just compare it with this Gaussian probability distribution of a pure diffusion process with this renormalized diffusion coefficient. And you see it matches the data pretty well. And the one other thing that we did do is we actually simulated the actual Poisson process of basketball scoring. That is that we took the probability distribution of a scoring event occurring with an exponential rate, and we also included the anti-persistence. And you see that this anti-persistence Poisson process fits the data incredibly well. So at least at this stage, we're making some progress in the sense that we can compare with real game data in a meaningful way and get some interesting behaviors about things like lead changes. So that's one small point. There's a number of other observables associated with this random walk problem and lead changes that are actually very subtle and very beautiful. Yeah, it's Laurent.
Very curious whether that anti-persistent parameter can encode bias in the random walk, right? Because when you just look at the data,
When you say bias, you mean like a global bias?
better than the other. So I just scored,
Oh,
and I just scored because I'm better. So
right.
it looks like it's persistent.
Well, okay, so everything here, I'm making the assumption that the two teams are entirely equivalent. And so this is a place where like real basketball fans will be already jumping on me like, that's not true. Like the Cavaliers are much better than like the Pelicans, which is a true statement. But please hold that question in abeyance because there is a bias, but I haven't talked about it yet. So let me come to that. But if I don't answer your question in about 15 minutes, like jump on me. Okay, so anyways, here's another amusing thing. How long does one team lead? So here is the trace. And this is actually one of the most amazing facts about random walks. And when I worked in random walks all my career. And after 10 years, I thought, well, I've been working on this for 10 years. I think I understand something about random walks. And I came across this, and I realized I understood squat. And this is a really beautiful property. You can ask, well, you see that Denver is leading all this time, then Chicago was leading this time, here's Denver leading, Chicago leading. You can ask, here's the green stick here, the green trace is the times in which Denver is leading. And so I can ask the following question. I can conglomerate these different time intervals, and so we see that Denver is leading, like roughly, 9/10 of the game. And you can ask, well, what is the distribution of the length of this stick? What is the fraction of time that one person or one team is in the lead in a game of a fixed amount of time? Clearly, if the teams are equally matched, the length of the stick should be symmetrically distributed about 1/2, right? Because if there's equal teams, then each team should be leading the same amount of time on average, but in any single realization, one team is leading longer than the other. So let's try and make a guess for this probability distribution for the fraction of time that somebody's in the lead. Clearly, it's a symmetric function. So what does it look like? If you think about like some random walk process where you're crossing the origin multiple times, you might think, and this is what I certainly thought, after 10 years of working in random walks, well, this distribution should be some peak function about 1/2. Most of the time, teams are leading equal amounts of time. It's very unlikely to have one team leading most of the time, or that's what I would have thought. Right? Doesn't that seem reasonable? Well, here's the data, and you see that it looks nothing like what I had in the previous slide, and in fact, it fits something called the first arcsine law. So this is now a zero parameter fit. I really like when you have zero parameters in any kind of modeling. So this is the time leading, and you see that this zero parameter fit called the first arcsine law fits the NBA data incredibly well. So this is surprise number one for me, is that there is this thing called the arcsine law, and if you've never heard of it before, congratulations, you've now heard of it. And it's a very beautiful property about random walks that even though there's no bias in the process, the fraction of time that the random walk lies to one side of the origin compared to the other is actually very much peaked at the extremes. Now, it turns out that there is a semi-elementary way to derive the first arcsine law, but there's actually a truly elementary way to derive the second arcsine law, and so I'm going to do that because it's simpler. And it's also related to another interesting question about basketball scoring, which is when does the last lead change occur in a basketball game? So again, we have our trace of scoring versus time, or score difference. And so there is some trace, and then you see that here is the last time the lead change occurred because this team finally won the game and there was no additional lead changes. So you can ask, when does this last lead change occur? Does it happen at the beginning of the game? Does it happen at the end of the game typically? What is the distribution of the times at which this last lead change occurs? So let's try and calculate it. And it turns out that it can be calculated by truly elementary means just with a little bit of knowledge of probability theory. So first of all, in order for a last lead change to occur at time t, it must be that the random walk, wherever he is at the origin at this time t. So we must have a return at time t. The other point, and this is the key to solving the problem, is that the trace that starts at little t has to never cross the origin all the way up to the final time. It ends at some arbitrary point x that we don't know yet. But if I imagine time reversing this process, we start at some unknown position x, and this random walk can never touch the origin until exactly at time t. It must touch it for the very first time, for this time reversed trajectory. So we have a return at time t, and then we have a time reversed, what's called first passage, because we're going to hit the origin for the very first time at this time, over this time interval. And as you'll see in a moment that these are both elementary things to compute. This is 1 over the square root. It's the Gaussian, which has e to the minus x squared over t evaluated at x equals 0, so that's 1. And then we have the prefactor 1 over 4 pi dt square root. And then for this return probability, well, here's the analytical form. But let me derive this because it's so simple to derive. And so this is sort of like, very first lecture in some course in random walks, which is that we know about where a random walk is. It's described by the occupation probability, which is just the Gaussian probability distribution. And I realize here that I've been a little sloppy in my notation because in my previous slides, I think I called this capital P for the probability. Here, this is little c for the concentration. It means the same thing. So this is the probability that a random walk is at position x at time t, just the Gaussian probability distribution. And what I want to ask, though, is a different question, which is not where is a random walk, but when does a random walk, starting at some arbitrary starting point, first hit the origin? And here's a very simple way to derive this, which is something that for those of you who have had any freshman physics class will know as the image method of electrostatics. So here is a trace of a random walk that starts at t equals 0, position x0, and is doing some random walk, and it hits the origin at this particular time. And I want to ask, what is the probability that it does it for the very first time? So again, the way you should think about this is you have a random walk on the positive semi-interval. At x equals 0 is an infinitely tall cliff, and if you hit the cliff edge, you fall over the edge and you die. And you want to ask, what is the probability that you're still alive at time t? And so I want to ask, when will I first die? If I hit the origin, I fall off the cliff and die. So here is the probability distribution without this condition that if I hit the origin, I fall off the cliff. And the way that you can then compute what is the effect of the cliff, it's the same as like thinking about a point charge above a grounded plane. You have potential equals 0 here, you have a point charge here, and the way you can you can solve this problem is that you forget about the grounded plane and you put an anti-charge equally spaced on the other side. So you start with another random walk, a negative random walk starting at minus x0, and it does a mirror image trajectory. And by doing this mirror image construction, you're guaranteed that at x equals 0, the concentration will be 0 because you take a Gaussian centered at x0 and an anti-Gaussian centered at minus x0. You add these two things up. This adds up to 0 at the origin at all times. So this is the correct concentration field in the positive x direction. And then all you have to do is compute what is the flux of people falling off the cliff. So you have to compute the diffusive flux, which is just the derivative of the concentration. And so that's an elementary calculation, and you get this quantity, which I wrote on the previous slide. Now, just as a matter of some intellectual interest, there are two amazing features about this first passage probability. First of all, you can ask that if I have my cliff over here and I'm a stupid random walker who's wandering around on my stage here, what is the chance that I'm going to die? Will I die for sure, or do I have a chance of living? Anybody have any guess? Should I try the experiment? Just get myself smashed and just wander around and put a manhole here and see will I live? Well, anyways, interestingly enough, the eventual hitting probability is equal to 1. I am sure to die. But the average hitting time is infinite. So even though I am sure to die, it takes infinitely long for that to happen. This dichotomy between being sure to go over the cliff and taking infinitely long time to go over the cliff is why one-dimensional random walks are still so amazing, so beautiful, so alluring, so full of life. So this is what got me interested in my direction of research, was this dichotomy. Okay, so now we come back to this problem. So we had our return at time t. We had our first passage probability, which was the same as what I had in the previous slide, except the time interval is capital T minus little t. And what I want to do then to compute the probability that the last lead change occurs at time t. So I have a return at time t, a first passage reversed starting from the end of the game at position x to the origin, which is this. Here are the two quantities. This is an elementary integral to do, and you just get the good old arcsine law. So this, again, is the arcsine law. It's called the second arcsine law, and amazingly enough, it's the same as the first arcsine law, even though it looks like it's a completely different quantity. So second arcsine law. Let's now look at the data. So here is the NBA scoring data, and you see that it is definitely like looking arcsine-ish with peaks at the extremes. And notice there's a little bit of anomalies here at 1/4, 1/2, 3/4 of the game. And so let's now try and do some simulation to try and understand this. So this is the result of just doing a good old homogeneous Poisson process. And what I mean by that is that we know there's an average scoring rate of 0.33. So I just flip a coin, and with a rate of 0.33, it'll be a scoring event there. And I just simulate a game, and then I look at where was the last lead change in the game, and I do this like millions of times, and I end up with this distribution of times for the last lead change, and you see it fits the data pretty well, actually. This is the result of an inhomogeneous Poisson process. So this is now getting more into the like fine print of basketball, because we saw that there was like an anomaly in the scoring events at the end of the first quarter, the end of the first half, the end of the third quarter, the end of the game. If you include that slight increase in the scoring rate, then you get these little glitches fitting pretty well. And then this is my favorite, my zero parameter fit, because there's no parameters anymore except the length of the game, and it fits the data also pretty well. So it seems as if we have a very simple random walk picture that's now describing some beautiful features about scoring lead changes. Now, one question you might ask is, why are there two peaks? Why was there a peak at the beginning of the game, at the end of the game? Again, before I had any insight here, the way that I thought about it was basketball is a bunch of really athletic guys running up and down the floor all the time, and they're scoring all the time, and so the scorer is just doing some kind of fluctuating event like this. So the last lead change should occur at the very end of the game. That's what I thought. And we see that there was actually something happening at the beginning of the game. And so let me give you kind of a physicist's explanation of why there should be two peaks, with a peak at the beginning and at the end of the game. So here what I'm showing again is sort of a cartoon of a typical scoring trace of a basketball game. So it's some random walkie looking like thing. But the crucial point here is, notice I'm plotting it versus logarithm of t. And the reason I'm plotting it versus logarithm of t is that random walks are a scale invariant process, and sometimes it's much better to look at things as a function of logarithm of time rather than as a function of time itself, and especially if you're dealing with looking at scale invariant events. And so, here's a typical trace, and here's where the end of the game happened to occur. So the random walk basically, I shouldn't have drawn this little glitch here because that's after the game is over. So the point here is that look where the last lead change occurred. It happened just before the end of the game. So here's an example where the last lead change occurred near the end of the game. Now let's imagine another game. And so I just draw another trace. And notice here that the last lead change occurred over here. It doesn't look very far away. But this is a logarithmic scale. So because it's a logarithmic scale, this might be orders of magnitude earlier than at the end of the game. So what you'll see is that if you, no matter what kind of trace you draw, that unless you engineer things incredibly carefully, the last lead change occurs like somewhere here, which is way far back in the past, or very close to the edge. And so this is why there's actually an unlikely event to have a lead change happen halfway through the game. Here's another thing which, again, for people, I've given this talk in England, and they really get into game time betting. I don't know if people are aware of this in the United States, but you can actually bet on the outcome of a game while the game is happening. And so here is a kind of a cool question you can ask, which is, what is the probability that I have a lead of L points with a time tau left in the game. What is the probability that that lead is safe? And with a random walk picture, it's really easy to compute because we just say, well, this lead is safe as long as the random walk, which starts from position L, never crosses the origin before time tau. But the probability of crossing is this first passage probability. The probability of not crossing is 1 minus the first passage probability. So I'm in a position to do this computation, and so here it is. So the probability that a lead of L points is safe with a time tau left in the game is 1 minus the probability that a random walk for the very first time, starting at L, will hit the origin before time capital tau. And so because this formula for f is known, we plug it in. This is an elementary integral to do. It's the error function. And so you end up at the end of the day with a simple analytic formula for this probability that a lead is safe. And also you identify what are the natural variables in the problem, because you started off with two natural variables. You had the lead, the size of the lead, and the amount of time left in the game. But it turns out those two variables don't appear separately. They appear in this natural combination of L divided by the square root of t. So this is a natural dimensionless measure of the size of the lead. And you end up with this error function profile. So let's just sort of give a flavor for what this is. So this is the probability that a lead of size L with time tau left in the game is safe, is this error function. And here's a plot of this safe lead probability as a function of this scaled lead size. And so you see that if the lead size is small, the probability the lead is safe is small. And when the lead size is large, the probability the lead is safe is close to 1. And to give you some numbers, here is to give you a feeling for this, is that if you have a 10-point lead with 8 minutes to go, you have a 90% chance that the lead is safe. So if any of you want to do real-time betting, then here's what you should do. If a team is winning with 10 points with 8 minutes to go and you get better odds than 90%, then you should bet on the team. Now let's look at the data to try and say, well, does this simple-minded picture, which seems so trivial, how does it fit the data? And so what I'm showing you now is this lead probability as a function of this scaled lead size. So here's the NBA basketball scoring data. Here is a stupid error function, which fits the data very well. And with apologies, because you generally don't like to trash anybody, but some of you know this name, Bill James, the inventor of sabermetrics, and this is a data science center. Presumably, many people have heard about this guy, and who did all this stuff with Moneyball and whatever. Anyways, he has his own heuristic way of trying to compute this lead change probability. So here's his heuristic, here's the data, here's our theory, so you can decide which looks better. Okay, so I'm kind of a little past the halfway point. I hope that I've given you a sense that in this very simple-minded way that basketball scoring seems like a plausible hypothesis to describe various statistics about basketball scoring. But there's some buts. And again, I guess nobody here really cares about basketball, because I've been in many audiences before where people are actually yelling at me by this stage of my talk. And why are they yelling at me? Because there's some buts, and I've actually swept them under the rug. But let me tell you some of these buts. First one we've already dealt with a little bit, which is this notion of anti-persistence. So after team A scores, the same team scores next to the probability roughly 1/3. So that's easy to take care of because it just effectively normalizes the diffusion coefficient. But there's another feature, which is that basketball, and if any of you have ever watched especially playoff basketball, you know how it goes. Like the first 45 minutes of the game, it takes about an hour and a half, including like the timeouts and the halftime. And then the last 2 minutes of the game, they're fouling all the time, they're sending in substitutes, they're timing out, and it takes 2 hours to play the last 2.5 minutes of the game. So there's something really weird about the last 2.5 minutes, both from the point of view of like when you watch it on TV, it seems like something is different, but the data also tells us something is very different. And so let's look again at our scoring rate. And so I tried to draw that like horizontal line around here, but you see that this is a huge increase in the scoring rate at the end of the game. It's actually much bigger than the scoring rate anomalies at the end of the first quarter, first half, and third quarter. In fact, the average scoring rate in the last minute of the game is a factor 2 higher than the rest of the game. So even though the game seems to slow down to the level of molasses, because there's always like fouling and timeouts and whatever, but by game clock, the scoring rate is actually increased by a factor of 2. And so here's another manifestation that this mean square displacement is obviously going down at the very end of the game. So somehow, if it's, there's a very strong bias at the end of the game to try and reduce the size of the lead. And here's another very amusing element, which is if you look at the actual probability distribution of the score difference at different junctures of the game. So what I'm plotting here is the probability that there's a score difference, actually scaled score difference. So delta is the score difference, and then it's divided by square root of 2 dt, where t is the time in the game. So this should be like a natural scaled variable, and this d fit is the diffusion coefficient of basketball scoring. And so you see at the end of one quarter, it kind of looks like a Gaussian probability distribution, which would be like a random walk process. At the end of the first half, because I've plotted it versus scaled units, the data again is another Gaussian, and it's basically overlaps because it's plotted in properly scaled units. At the end of the third quarter, everything is fitting on top of each other. At the end of 45.5 minutes, it looks almost the same. You see there's a little bit of enhancement over here. And then at the end of the game, this happens. So the last 2.5 minutes of basketball have nothing to do with the first 45.5 minutes. Okay, so that's the last 2.5 minutes are anomalous. Here's another question, which Laurent already asked, which is that there's a bias. I mean, why did I treat this as an unbiased random walk? Because when the Cavaliers play the Pelicans or whatever, doormat team that happens to be that year, the Cavaliers, in fact, since I come from Boston, I lived there for 42 years, and I was there during the golden years of Larry Bird. And so in Boston, we used to call the Cleveland Cavaliers the Cleveland Cadavers when they played Boston, because they were dead the instant they stepped on the court. So anyways, the teams are unevenly matched. So how do I include the bias in the process? So let me just say a few words about this, which is, first of all, even though there's bias, think about the worst team in NBA basketball. The worst player on the worst team in NBA basketball is a 100 times better athlete than I'll ever be. So these players have come through high school, through college, they've been drafted in the NBA, they survived the training camp and the cuts. So there's been an incredible level of filtration. So even the worst player playing in the NBA basketball is incredibly good. And the difference between the worst and the best player is truly not that large. I mean, everybody can dunk, everybody can do all these things that I can't even imagine doing. So even though you say, well, these teams are losers, these guys are bums because they can't play. I mean, they could kill us, no problem. I mean, take any random physics department and put up a basketball team, it'd be pretty hopeless. So they're not that, and so the point is that they're not that unevenly matched. And as I'm going to argue to you, the differences don't even matter. So let me give you a sense of that, which is let's look quantitatively at the role of unevenly matched teams. So I did some theoretical calculation for you, looking at things like the arcsine law. And we can do the same thing. Here was the arcsine law, which is the probability that the last lead change occurred at time t in a game, which is this U-shaped distribution. So this is what happens if you have equal team strengths. But if you have unequal team strengths, it turns out you can do the same calculation. I'm not going to show it to you because it's like more horrible, but it's doable. And what you find is that you get a more complicated looking object, but it's an object that has the same qualitative feature, that it's a U-shaped curve. And what I'm showing now is the U-shaped curve associated with imagine that I have two teams that are biased so that there's an average velocity associated with the trace of my random walk. And the velocity, I'm choosing 0.002, 0.004, which is actually the true average velocity. If I take all possible NBA games, look at the final score, and say, well, this team won 120 to 100, so that meant that there was a 1.2 advantage of the better team over the worst team. And then I compute what is the average bias over all basketball games. It turns out the average bias is 0.004. And I'm looking at the same arcsine law, and you see that if I have a bigger bias than what's reality, you can start to see some skew in this arcsine law. But at 0.04, it's barely visible skew. And then the thing is that what I should do is I should take every single... Does that mean I have to stop?
It means you're about 45, 50 minutes in, so maybe another 10 minutes.
But I started at 3:30. It's only 4:05. Oh, no, it's 4:20. Oh, wow, I see. Wow, that clock is... I'll go by that clock.
Okay, sounds good.
Anyways, so the point is that I'm not sure I was in my train of thought here, but it's just that every single basketball game there's a little bit of a bias, and then I should average over all possible biases. And when you do that, you end up with the same arcsine law as before. So averaging over team strength doesn't do anything. There's another feature which is kind of amusing, which is there's a feature of return to zero. If a team races out to a 40-point lead, what do? Well, the team that's in the lead sends out its subs because they want to rest their starters. The team that's behind is desperate, and they start launching three-point shots and fouling. And so there's a systematic difference in the scoring probability as a function of lead size. If you have a 40-point lead, your scoring rate is only about 0.42. If you're 40 points in arrears, your scoring rate is about, or scoring probability is about almost 0.6. So there is another element to this, which is that there is a sort of spring which is trying to make the score being tied. And so this allows us, all these features allow us to build a detailed computational model of basketball scoring. And so there's something called the Bradley-Terry model of competition. And so the basic idea is as simple can be. You imagine you have an ensemble of teams of strength x sub alpha, so that's the strength. And what you want to do is, given the strength of two teams that are playing, what is the probability that one team wins? And so this is the Bradley-Terry model, that if I have a team of strength XA playing a team of strength XB, the probability that A wins is XA divided by the sum of the X's. So if XA is 1 and XB is 0, then team A will win for sure. If they're both equal,